Yeah, it's nice to be here. I worked at Stanford until about 3 years ago, and then I moved. Um, but it's good to be back, familiar faces and familiar places here. So today I'm going to talk about unconditional concrete lower bounds for this modular squaring operation. Okay, so just to uh, clarify the problem here, so I'm going to call it squaring mod m. We're given an n-bit positive integer x and an integer m between 2 to the n minus 1 and 2 to the n. And we want to compute x squared mod m. All right, and I've been told that you all know why. So, so, so I don't have to talk about that, do I? Great. So Donald and Justin they were in my office a few months ago and asked, can you prove depth lower bounds on squaring mod m? So can you prove that any logical circuit is going to require at least a certain depth for this? And so me immediately was like, yeah, of course, no problem. I mean, like, why not? I mean, no. I mean, like, actually, complexity theory is infamous for being very hard. P versus NP and the like. But there are some things that we actually know. Okay, there's some, there are things we know. Okay, so in this case, there are things we know. It just can take us a little while to know them. Okay, so a few months pass, and then like me a few months later, okay, I figured it out. All right, but yeah, I have no idea about depth lower bounds for this x to the 2 to the t mod m thing. Okay, whatever. Okay, that's let me say up front. But this is, but yeah, there's some ideas, but yeah, I don't know about that. But this squaring mod m thing, you can definitely prove some interesting limitations on it. Okay. So I'll talk about worst case lower bounds and average case lower bounds. So this worst case is just any circuit that's computing on all possible instances needs at least a certain depth. Okay, so the concrete theorem is for every logical circuit over the OR and NAND fan into, so anything doesn't include, say, XOR, computing squaring mod m on all n-bit integers requires depth at least about 2 log n. But I'm including all the constants because I heard you like constants. Yeah, so that is it. In fact, I proved that constant from 4 from yesterday. It was 6 or something. Yeah, so for 2048, the depth is at least 12. So you stick in 2048, you get 11 point something, but depths can't be non-integral, so it's at least 12. Yeah, and the depth is at least 10 for n equals 1024. Okay, and so the idea is actually to reduce this to a seemingly much simpler operation, the sum operation. So here I'm taking n bits and I'm outputting about log n bits, like the actual just sum of the bits. And the conjecture that I guess I'm going to make is that for all n, sum needs depth at least 4n log n. Now this theorem here is unconditional, okay, the thing in the blue, okay, to be clear. And it's known to have depth at most like 4.14 log n, and this actually from a few years back, and people have been chugging really hard at like improving that constant. But once you can compute sum, you can compute any symmetric Boolean function, and some of these look pretty difficult. So like the majority function, for example, you would easily be able to get from that. So we can show that in fact this conjecture would imply like that everything gets multiplied by a factor of 2 here. And so because of this non-integral thing, that means the depth would go up to say 23, because it would be say 11 point something, and be 22 point something down there. All right. And I want to emphasize that these results hold in the most general sort of abstract model where circuits can be arbitrarily connected. There's no like VLSI type physical constraints, and that's something I would like to talk about, like how to prove that, say, no computer the size of this room or the size of Stanford Stadium like needs at least so much time to say do squaring or repeated modular squaring. That would be great to do. But yeah, so the point is these are conservative lower bounds. They should be much higher than this, I think. But this is going to be close to the optimal for at least squaring, because I think for squaring you can get something depth like 5 log n actually for squaring. So like if you just wanted to like square. Okay. So average case lower bounds. So these are, I would say, fairly weak, but at least we can prove something unconditional. But I think it can be improved drastically in sort of both these parameters. So we say every circuit computing squaring mod m correctly on at least 76%. It's important that it's greater than 75 of all n-bit integers requires depth about at least like log m minus 2. Okay, I think that both of those, red pieces should be improved. Like it should be that like even like any decent fraction, like you're outputting so many bits, so even maybe 1% should require like some decent constant times log n depth. Yeah, intuitively, I think the depth of lower bound should be about as hard as the worst case, but our proofs in the worst case don't extend for various reasons. So this lower bound applies an interesting theorem about the sensitivity of squaring mod m modulo 2. So this is computing the least significant bit of this squaring mod m function. Okay, so in fact, like the theorem holds for just computing like the low order bit of modular squaring. Okay, so this is a theorem by Benjamin. I hope I stated it correctly. Okay, so for all large n and for all odd m, there's at least n over 4 distinct inputs, okay, into the squaring mod m function. So the squaring mod m function has n inputs. There's at least n over 4 distinct inputs, such that on at least half of the n-bit inputs, or very close to that, the function is sensitive at the ith bit. So in other words, for each of these i's, if I flip the bit there, the function value will change. And that's true for half of the inputs. So the ones I can specify n over 4 bits up front of the input variables, so that on at least half of the inputs, when I flip just that bit and leave the others the same, the output must change. Okay? So this is the kind of result where you want to say that, okay, this function is sensitive on many inputs, so it must depend crucially on many inputs, even in the average case. Okay? So full disclosure, I had conjectured a stronger statement to be true, that essentially there are n, essentially all of those bits are going to be very sensitive, but Donkrod and others show by counterexamples this is actually false for many, many m. So this is interesting. I mean, that's just saying with the low order bit, how hard is the low order bit of squaring mod m, and we're not talking about the others. So almost certainly one can prove stronger depth lower bounds if we study, say, different or more, study all the bits of the output rather than the least significant one. It's just the least significant one happens to have nice little properties that make it interesting to look at. Okay, so those are the two flavors of results that I have. Oh, right. So I'm the guy between you and lunch. So when should I start wrapping up? I mean, I think I've only been speaking for a few minutes, but maybe I should know.
Please continue.
Okay. All right. Okay. I will continue the talk. Fine. So I want to tell you sort of all the big ideas behind these, hopefully succinctly. So let me talk about the worst case lower bounds, how we prove them. Okay. So the idea here is we're going to prove limits on integer squaring with no modular reduction, and in fact, just proving limits on integer squaring, it only loses a constant factor in the depth of our lower bound. We lose with this log n because of something else that I'm going to talk about. So here's going to be like a one-slide proof sketch with sort of all the ideas. First in lines and then in pictures. Okay. So the first claim is that every depth d circuit for integer squaring on capital N bit integers, where capital N is about n log n, little n log n, this can be used to get a depth d circuit for this function, n-bit function sum. Okay, so in other words, just by plugging in 0, 1 constants in the correct places and plugging in your x sub I bits in the correct places, you will get a circuit for sum. Okay, so it's like some kind of reduction by projections. Okay, All right, so we're going to use that. And this n log n is kind of where we get this minus log factor here. Because the next step is that this sum function is known to require depth at least 2 log n, okay, on m-bit numbers. But see, this little n here is different from this capital N, so we'll lose a bit in the depth. In fact, it's been known since the 70s that even the low order bit sum, computing the parity, the sum modulo 2, is going to require depth at least 2 log n, and that's tight. I mean, you can also compute it in depth 2 log n. All right. So 1 and 2 together tell us that, oh, well, that means if I had something for integer squaring, I have a lower bound on that too because it could compute some, okay? So just plugging in, just substituting capital N for little n, we get this depth lower bound on integer squaring. So there's no modular reduction, all right? And then there's a very easy observation that every depth D circuit for squaring mod m on m bits implies a depth D circuit for integer squaring as long as I set the number of bits to be small enough. So as long as I make, the number of bits to be log of the square root of m minus 1, then I have a circuit for integer squaring because there's no modular reduction at all. Okay, like if the numbers being input are say less than square root of m minus 1. All right. So, then if we combine 3 and 4, then we get and calculate. We stick in the fact that we are assuming m is, say, greater than 2 to the n minus 1, then we'll get the claimed lower bound here. Okay? All right, so that's the high-level idea. So it's a series of what you would call reductions, I guess, in complexity theory.
Right?
Yeah.
Instead of squaring, you use powers of 4. Then is it just a matter of generalizing the first claim, or is it more than that?
Oh,
So fourth power rather than squaring.
Yeah. Okay. So, yeah, I don't know. It would boil down to how we need to modify this embedding trick here. Yeah, so claim 1. Claim 1 is really the only, the other stuff is like just plug and chug kind of like, yeah, but claim 1 is the sort of the interesting bit here. In fact, I'm not sure that n log n should be optimal even for squaring, but for, raising to the 4, I'm not sure. I haven't thought about it, but maybe it will be evident to you from the proof outline I'm going to give. Any other questions about this? I'll give like some sort of picture version of this line by line thing too in a second. Yeah, Ellie.
How far is it from the known upper bounds?
Oh, so even for integer squaring, it's at most like 5 log n. So integer squaring with no modular reduction. I think. It's pretty close, but I think that if we had this lower bound on the sum function, which I think is natural, then I think it would be very close to optimal. Yeah. Okay. All right. So how would we generalize this to this conjecture about sum? So assuming this sum function needs depth at say at least c log n, well, we would just stick it in here. If it needs, like everything, just substitutes in, right? So it's really just a reduction to this lower bound that's known for computing sum. But I think sum should, in principle, be an easier problem. It just so happens to be easier to prove a lower bound for too. Like easy in a different sense. Okay. All right. Okay. So here in picture, so the idea is we start with a circuit for squaring mod m for sufficiently large modulus. Okay, and it takes n bits, and it's got some depth d of n. We want a lower bound d of n. So this is just a summary of the previous thing, but with some pictures. All right. So the idea is that, well, we could trivially get a circuit for integer squaring if we zero out the first half of bits. Okay, like we just zero out the first half of bits. There is no modular reduction, happening, and this would still be d of n. Okay, so this is now something for integer squaring on only n over 2 bits. All right, and now the interesting thing is that we can plug in zeros in almost all of this circuit except for about n over 2 log n of the bits. And now we have a circuit computing sum on m bits, where m is about n over 2 log n. Okay, but for sum, we know that the depth is at least 2 log the number of inputs, which is n. All right, so we just go back and we can figure out, oh, this d of n must be at least this function of n. Okay, just relating m and n. Okay. Good. All right, so let me give you an idea about how you prove this claim. So if I've got some circuit for integer squaring, how do I get one for the sum function? All right. The idea is to show that the middle bits of integer squaring can compute sum. So integer squaring is taking n bits and it's outputting 2n bits, right? It's a square. All right, so we want to show that the middle bits can compute it. Okay, so suppose we're given an n-bit input x presented to us, in this form, like binary form, and we want the sum of its input bits. Okay, so the idea is that for sufficiently large k, so make it like 2 plus log n, we're going to find a number z with respect to this number x. Okay, so it's like a bunch of powers of 2 to the k, so 2 to the ki for various I, and then in the top half of the powers of 2 to the k, I'm going to put the bits of x sub I in there. All right. So visually, what's happening? We're creating a much larger, n log n length bit string that's mostly zeros. Okay, but it's got the bits of x spaced out in like the high order parts, and some ones spaced out in the low order parts. Okay. All right. And the claim is that the quantity, sum of I xi, as a bit string, is contained in the bit representation of x squared, of z squared, okay? To see that, it's probably easier to consider this power of 2, this 2 to the k, as a variable, and think of a polynomial, p of y, where we just have an indeterminate y in place of that 2 to the k power, okay? And so we've got like the coefficient 1 on like all the terms from 1 up to y to the n minus 1, and on the higher order terms, like the higher degree terms, we put the bits of x, okay? And so if you look at the square of this, okay, what's going to happen in like the middle coefficient, y2 to the n minus 1, it's going to take exactly, let's see, is there a, okay. All right, is there a pointer thing? Is there a, there's no, okay. Yo, the mic. So, yes, hello. Okay, so the point is, in this coefficient, right, you're computing a sum of various products of pieces from this thing. You'll take exactly one of these times exactly one of these, okay? And you'll do it twice for the 2 possible ways to pick, this, like a pair of one from here and one from here, and the opposite way, all right? So that will give you exactly the quantity you want, times 2. But we're working in binary, so that just like, times 2 just goes somewhere else. And so if we plug in a sufficiently large number for y, okay, then the point is that all the different contributions to this product will be kind of spaced out in the string, and they won't interfere. There won't be carries that will interfere with our desired quantity of the sum over ix. So we just stick in a large power of 2. Those will all be spaced out, and each little term will collect separately. No carries will interfere with it. All right, that's the idea. And so by hard coding appropriate zeros and ones into a circuit for integer squaring, we'll get a circuit for sum. All right, so that's the high level idea. Okay. It's the trick has been used before in other contexts in circuit complexity, but maybe not for exactly this thing. All right. Okay, so now I want to say a little bit about how you prove the average case thing, and that is different. Look at this. Just in case I need to like move around somewhere. All right. All right. So this uses some other methods that were known in circuit complexity. So given an input, an n-bit input, let x to the I denote x with the ith bit flipped, and that's just literally what you think it means. You flip the ith bit of it. So I ranges from, say, 1 to n. All right? So we say that a function f, so a Boolean function from n bits to a bit, is degenerate in k variables if there are distinct indices, so distinct input variables, say I1 through IK, so that for all the possible inputs I could feed into F, flipping any one of these I1 through IK is not going to change the value of the function. So f of A is equal to f of A with the ij bit flip for all j. Right? So in other words, there are k different input bits, different variables of f that do not affect the output at all. Okay? So this is like some degenerate case, and in fact it's degenerate in like multiple variables. Right? So one fact, this is from the Stanford class CS 354, which you might remember. Okay, Hart. Okay. So it's like every minimal circuit. It's a generalization, in fact. Okay, so every minimal circuit with at most n-1 minus k gates is degenerate in at least k variables. Okay, so the idea being that if my gates are fan in 2 and my circuit is small enough, there's just not enough gates to even cover all the input variables. Okay, and so like some inputs are just going to be disconnected from the output. And so they can't affect the output if they're like not even connected. All right? And as a corollary, you can also say, well, every circuit with depth at most log of that quantity is also degenerate, because if it had smaller depth, then if they're only fan-in-2 circuits, then they could only have at most so many gates pointing to inputs. All right? All right? So this is already saying that like anything that goes below log depth is going to become really simple really quickly, like depending on what you set your value k to be. All right, so concretely, we're going to say, look, every circuit with depth less than log n minus 2, so that's like what we want in our lower bound, is going to be degenerate in about like 3 n over 4 variables. So like most of the variables, this is going to be degenerate. All right. And so the idea is to show that there's at least n over 4 variables of modular squaring, even in the least significant bit, so that for almost half of all n-bit inputs, flipping each of those variables does affect the output, right? So we want to show that for these n over 4 variables, flipping any of them will affect it, okay? So then this is where Benjamin's theorem comes in, so that there's going to be n over 4 variables, so that this squaring function is going to be sensitive on at least half of all the possible inputs. Right? And so finally, the point is that every circuit of depth less than log n minus 2, because it's degenerate in so many variables, it would get at least half of those inputs, like whatever ones which it does affect the output, it would get at least half of those wrong, okay? Because it's giving a different value on the parity. So because it does affect the output, it's giving say 1 on one of those inputs and 0 where the ith bit was flipped. But the ith bit is degenerate, right? So the circuit, if it's degenerate in that variable, it's going to output just 0, 0 or 1, 1 on these sensitive inputs. So it will get at least one of those wrong. Okay? So we're saying like so about half of the inputs, it will get half of them wrong. Right? So that's how we get like, okay, it gets a fourth of them wrong. So anything that gets it correct in at least 76% is going to require that depth. That's a high level idea. But yeah, I mean, this is meant to be improved. Like I'm communicating this to you to see, so you can see like, wow, that looks weak, that looks weak. So like it's meant to be improved upon, I think. Okay, like both the percentage and the depth, right? But I guess the main point is that such theorems are possible. They can be proved, and it doesn't take, P, equal versus NP type stuff to prove that kind of thing. All right, that's all. Thankfully, okay. All right, so let me wrap up with a few open problems. Okay, so again, almost every result here is suboptimal, except for like the thing about parity that really does take 2 log n depth exactly. Okay. So there's lots of room for improvement, but almost everything that was interesting here is suboptimal, I think. Another thing is that the best known unconditional depth lower bounds for simple functions are actually at about 3 log n, not 2 log n, but they're for different weird functions. And I have been thinking about a while, like could you somehow use this circuit for integer squaring to implement these weirder functions? That's something that would automatically get you a better depth lower bound for that. Maybe there's a better lower bound for the sum function, which is at the heart of the worst case thing. can we get better average case lower bounds on other bits of squaring mod m, like taking the middle bits or taking the majority bit of squaring mod m? That seems possible. I want to say that the worst case lower bounds, they're not going to work because if you look at the inputs we're feeding to this integer squaring circuit, right? Like first we like stick in a bunch of zeros for half the inputs, and then we stick in like a bunch of like ones spaced out. Like so, most of the inputs that we're feeding to the thing are like full of zeros. So it's not like average case at all. Right? So that's very far. It's a worst case lower bound, but it's very far from like something interesting on average. Obviously, another interesting question is to prove lower bounds on different integer representations beyond binary. I mean, this stuff about degeneracy, this doesn't. I feel like this is something that is so basic. It's kind of it feels independent of like the representation in some sense. Like unless like the answer is already encoded the input for you. Like if you're doing any interesting work, then like something should be non-degenerate. Okay, something should depend on all the input bits in a crucial way. In which case you always get at least a log n lower bound. So I think a lot could be done there. What about more constrained real-world architectures? Like I didn't assume anything about how things are connected, make any interesting assumptions like that, like VLSI type assumptions about how stuff can be connected. That would almost certainly prove something stronger than what we've got. Finally, I'd like to ask, is there any natural assumption implying good depth lower bounds for, say, like this x to the 2 to the t mod m? Maybe hardness of integer factoring? So to me, my intuition is that, so for example, the Blum-Blum-Shub PRG, this is exactly modular squaring, if you know what this is. So like you're taking a seed and you square it and you modular reduce and then you output, say, the parity of it, the mod 2-bit. This is exactly why I was looking at the mod 2-bit, because like this is the thing you output in Blum-Blum-Shub. And so the point is that like just outputting these bits, somehow this is going to look pseudo-random if factoring is hard. So it is natural to think that this repeated squaring thing should be similarly hard. But yeah, anyway, to me. Okay, that's all. Thanks. Oh, sorry. Is that Riyadh?
Yeah.
You grew a lot of hair since I last saw you, so I like had to
Maybe this is naive. In the average case, it seems like this is quantifying universally over M, but probably many in this crowd would be happy if
I think
okay.
Hey there. So in the average case, the statement quantifies universally over M, but probably most people here would be happy with like a class of M where you can get something better as long as that M is useful, like a semi-prime. So is there any hope for something like this? Like, should we expect to be able to say, well, as long as your M isn't too bad, maybe you can do much better in terms of the average case lower bound?
Yeah. So there are lots of things that I did that I have not given the talk about. Like, so looking at like M's, which are the products of 2 primes, you can prove worst case kind of lower bounds, which are interesting, and more along the lines of the sensitivity stuff. But they're a lot more involved, and they don't seem to actually get much more advantage beyond like these sort of simpler ideas that go up and just reduce the integer squaring. But yeah, for the average case, I think that's probably where progress would be made. So like restricting to M's that are, say, the products of 2 primes. Like because in certain cases you can get nice results that generalize like the prime case, like in terms of computing sensitivity of various functions modulo PQ. Yeah.
You probably want in the lower bounds to have like a succinctness as a part of the trade-off, because if you allow unary representations that are very inefficient, you can just have depth 1, right? It's basically an and, like, basically
Univariate representation?
well, just no unary.
Unary.
Like a
course.
unary representation where the depth will be like 1 for any integer.
Yes, of course. Yeah.
So like maybe there's
Certainly. I wasn't saying that every representation. Yeah, the representation which include the answer is also depth 1.
No, I meant okay. What
Yeah.
I mean is, if you allow certain unary representations for your integers,
Okay.
then it's not that the answer is already encoded, but you'll have a circuit of depth 1 that basically is just a bunch of ands that will give you what is the
Yeah.
So
Yeah. I mean, now you're exploring the fact that like I only care about one input of length n. Right. Like Like if it's unary representation, I only care about one.
No,
I can
no,
compute,
it could be a
I can
family.
compute any function, even undecidable ones that are only
In
on
binary
unary.
representations, you allow up to 2 to the n different integers.
Yeah,
right?
yeah,
But it's fixed
exactly,
For that. So
exactly.
in unary, you allow up to n different integers.
Oh, I see.
There are certain
I see.
unary representations,
Okay,
right? That let's say
I see. But I guess any function whatsoever in unary representation would have a poly-size circuit at least, right?
Yeah. All I'm saying that
But
maybe there's a trade-off that says
Okay.
that for that the lower bound will hold for very succinct representations. But
Uh-huh.
if you allow a lot of redundancy and not as succinct, actually
Absolutely.
you expect the depth to go down.
absolutely. So the theorem approaches of Fropchenko use the fact that like there's many inputs for which like if I flip a bit, it's going to change in this certain way and so on. Yeah, I mean.
Okay.
That I think that has to play a crucial role in any lower bound. Yeah.
And kind of adding on that, if you allow M to be highly composite, you could take a Chinese remainder basis and also
Absolutely.
get a very low depth circuit.
Absolutely. Yeah. Yeah. This is sort of, yeah. I mean, this is like somehow working in CRR, we would almost be forced to look at repeated squaring before it becomes interesting, because if we only do like one square and there's enough moduli and things, they're say big enough, then yeah, it will just be low depth, right? Okay. Thanks.